we are back, and I had a few questions in the chat. So quickly before I cover this other question I wanted to cover, let me see. So Saide, I don't think I've shared with you the final exam from 2016. Maybe you mean 2015? And Ajimon says, wow, okay. We just saw this maximum likelihood estimation problem where the parameter theta was a scalar. The parameter theta was a scalar, and Ajimon's question is, what can we do? Sorry, I need to focus here. What can we do when theta is not a scalar, and when theta is not just one number? It's 2 in that case. We have theta 1 and theta 2. So in that case, you have a system of equations, right? Again, the principle will be the same if a solution is available. If a solution is available in the form in the closed form, as we say, right? Then it will be a system of equations. And just to show you real quick here. 1 second. Right, so we have this principle. We say we take the derivative with respect to theta and we set it to 0. Now, when theta is more than one number, it's a vector. We typically will represent it as a vector. And in that case, we will have, if theta is a vector in R to the D, let's say, then we will have that we set the gradient of G with respect to theta, we set it to 0. And then we have a system of equations, as we say. So this 0 here is a 0 vector, right? It's these zeros stacked on top of each other. So this basically here is a system of D equations, and we need to solve the system. As luck would have it, we're about to do one of those. Okay, so in the next question that I wanted to cover, it's a very nice combination of maximum likelihood estimation, another view on regression, and because those topics are also there in your exam tomorrow, this next question is very important. And it also, even though it doesn't really solve the problems that you will see tomorrow, but you will learn a lot of, it will still be very helpful, and it will answer Ajimon's questions. Not tomorrow. There's no exam tomorrow. Sorry, Benjamin. There's no exam tomorrow. Your exam is on Thursday. My bad. I misspoke. That's right. That's right. Okay. Okay. So let's look at this other question. But I guess I can address Aladdin's question regarding derivatives in general. Are we supposed to know all of the basic forms, rules, like trigonometry functions, for example? I don't want to fill my precious cheat sheet space with all of those. I mean, that's a good question. No, things are not getting very exotic. Things are not going to get that exotic with respect to derivatives and stuff. I can tell you that you don't need trigonometric functions and stuff like that. It's going to be simple things that we have already seen, and I'm gonna leave it at that. Okay. All right. So all right. So this other question is a very cool. I guess I don't know that this is. I will not give it to you exactly in the form of a problem, but this can be turned into a problem. I will just tell you that the questions you will have on your exam are not going to be this, but this is very helpful because it combines regression, it combines maximum likelihood estimation, which are things you will see in your exam. So okay, so let me move my windows around. All right, so the main thing here is that this is super nice connection that says we can come up with the regression rule basic regression loss even, which is the square loss or quadratic loss, we can motivate it from a maximum likelihood estimation viewpoint, okay? And it's all about the right assumptions here. And it looks like this, okay? Let me start writing things down. We're going to make some assumptions on the distribution that generates our data. So we start with assumptions. We're going to say first, before we narrow down things, very generally, we're going to say that there exists a, let's say, a function f star of x such that all of our labels for our regression look like this. And this is epsilon. This last letter I wrote is an epsilon, and it's noise. It's basically, it's a noisy model that says for each example that we draw, we're adding a little bit of noise of variance sigma squared. Okay, so what is the process here? This is our very vague assumption. We're going to make it more specific. We say that we start with the x point for this particular regression problem. So someone will give me an x. I will push it through this ground truth, as we say, through this data generating function. There's a few different ways to say that. This true f that will give me some number here. I will add some noise, independent IID for each example, right? Which is Gaussian, and that will be my final label. Okay, that is a common model for regression, how data is generated before we do regression. Okay, and there's another way to write this, I guess, which might be helpful, with slightly abusive notation, if I may call it that. That y given x, we're basically making an assumption on this conditional distribution on y given x. We're saying, under some kind of weird definition of this equality sign, that y is basically a Gaussian with mean f star of x and variance sigma squared. That's it, basically. That's our high level assumption. Okay, that's what we're assuming about our data. And now we're going to make it more specific. We're going to step 1 and step 2. We're going to actually zoom and go focus on linear models. So the second assumption is that there exists a theta star such that f star of x is actually x transpose theta star. Okay, so this true function that is giving me my labels y is actually a linear function. And the assumption we make, we're skipping the bias. It's easy to handle the bias, b, the constant, but we're skipping it for simplicity now. Or we can hide it in theta by extending our x, or augmenting our x, as we've seen at some point during the class. So, okay, so we're making this assumption, and we say that we're going to learn from this hypothesis class of just the linear predictors. So this hypothesis class f, sometimes we use a calligraphic h. I'm using a calligraphic f. It contains all predictors that can be written in this form: x transpose theta for some theta in r to the d. Yes. Okay. So what's happening here implicitly? Maybe I haven't. Let me getting some notifications here, and that shouldn't be happening. So for this to be true, I guess I skipped one little thing about the specifications up here, the assumptions. Our data lives in R to the D as well, okay? Our data points are d-dimensional. So then for this inner product down here to make sense, we need theta to also be d-dimensional. So we can write this inner product. Okay, so these are our assumptions. So now, okay, let's say that we're given data. Someone is giving us data set x1, y1, x2, y2. We get n of those, xn, yn. There it is. And we're going to use some helpful notation. I'm actually going to say that calligraphic X is the collection of all X's that are in my training set, okay? This is my training set points. It's not all possible values that it can take. It's all the endpoints that I've collected, the input points X, and the labels Y. I can use a similar notation to call the collection of Y1 through yn. We can call it calligraphic Y, okay? So now, basically what is going to happen is we are going to do maximum likelihood on this. Let me show you. We're going to take this likelihood, basically the set of all labels in my training set, condition on the set of all input points, set of all input points in my training set, calligraphic X. And then I use this other notation, okay? I'm gonna zoom in and explain, but basically, this is conditioning. We're saying that the distribution of all of the Y's that I have collected in my training set, conditioned on all of the X's, and then the distribution that we use to calculate this likelihood is parameterized by theta. So this just tells me I'm parameterizing this distribution by theta, right? Rather than conditioning. So this is not a part of the conditioning. This is a parameterization. Part of the conditioning is we have these variables X here, all of the training input variables X, okay? So now, basically, the thing that we're going to show, and it's quite simple, is that if I do maximum likelihood estimation of theta on this conditional of the Y's given the X's that I have collected, we get least squares regression. That's it. We didn't do that in class, but that's a very nice commonly discussed connection. And it's also an opportunity for us to do another exercise of maximum likelihood estimation. Okay, so let's do that. Let's do that. I'm going to just write out what those Y's and X's mean. Again, the Y is the collection of all labels I have collected in my training set. The calligraphic X is the collection of all input X's in my training set. So this, I'm just writing out the same thing. And then this distribution P, again, is parameterized by theta. Okay. Why is my distribution parameterized by theta? What kind of assumption? What is this distribution, right? I've told you a lot of things, and maybe you're a bit lost by now. What is this distribution that is parameterized by theta? Let's go back here. Let's go back here. We have made these assumptions. Let's look at our assumptions again in light of what we're trying to do. Always go back and check your assumptions. The assumption is that the data is generated in this form. Assumption number one, there exists some ground truth F star. And assumption two is making it more precise. It's telling us that this F star is actually can be written like this. Okay. So basically, and part of assumption one was this. Assumption one is actually giving us this conditional distribution that we want. We didn't write it explicitly here, but this is actually the way it's written. It's a parametric family. So I can delete this and I can expand it. I can say, actually, okay, what's the best way to do this right now? I think I will just write it again, taking into account both assumptions, okay? But taking into account both assumptions, the final form of my parametric conditional distribution here is this. We have a theta, okay, and we have a sigma star. But let's assume that sigma star is fixed. Someone is told us what the value of sigma star is to make our life easier. Let's assume that sigma star is a given, because that's slightly less important here, okay? And sigma star is a parameter of the data generating process, but not of our model necessarily. So what we want to focus on is theta, which parameterizes our model. Okay, so this theta here is the basic set of parameters for the model we're learning, and it's also, you know, how we parameterize this distribution. So what have we done here? In other words, we have assumed that the data is generated like this, and we said, okay, fine, since the data is generated of this form, and assumption 2 is telling us that it's a linear function, it's an affine function, I guess, then we're going to learn from this parametric family. So the conditional distribution induced by, you know, considering models of this form is parameterized by theta, like this, okay? Does this make sense as a parametric distribution? Right, it's the conditional of y given x. So now that's why we have this parametric form here, and we've written out, we've expanded this calligraphic y, we expanded this calligraphic x. It's just all of the labels and all of the input x's, and then what's happening? There's one thing we don't like here. In order to simplify our life, we wanna break down those big joint distributions. So joint distributions are a pain. All of those y's together, all of those x's together. So we can indeed simplify things here by taking into account how the data was generated, right? So we're assuming again IID data, okay? But before we can say that much about it, we have to take into account the complete form. And so we will have, the most important thing here is how the y's are generated, right? And let's zoom in, because it's a conditional. So let's zoom in and see how the y's are generated. They're generated like this, meaning that and we have this form. So I'm going to write it again down here for simplicity. Yi is given by xi transpose some theta star plus epsilon I. So for each example I that we're generating, someone is giving us an xi. We're taking the inner product with theta star, and we're adding an independently drawn Gaussian variable with 0 mean and variance of sigma squared to add here. Okay, that's how data is generated. So basically what this is telling me is the following with respect to what I need to do here. Yi is basically conditionally independent, sorry about that, of other x's, xj, given xi. This is, I'm not sure if I use this notation a lot in the class, but this is one way to write conditional independence. And that's the notation. It says that if I condition on this variable, xi, then these other two variables are independent. So this kind of symbol we use for independence often. Okay, if I condition on xi, then yi is independent of xj. That's conditional independence. Why? Because we can just see how yi was generated. It just depends. It just depends on xi. That's it. It doesn't depend on xj, etc. Does this make sense to people? In particular, we're not examining here whether whether xi and xj are dependent or not. I don't want to spend too much time discussing this, but in this whole set of assumptions, we haven't said much about the distribution of x's. It doesn't matter, it turns out. In this particular exercise, the way we've set things up, it's only the conditional, this conditional that matters. The distribution of x's does not matter, really. Okay? But this is all that matters, how the y's are generated from the x's. Okay? So coming back here, all we need here is this conditional independence to say that yi only depends on xi. Okay, so if I'm given xi, any other values for xj, xk, xl, they make no difference on the distribution of xi. Oh, sorry, of yi. So that's exactly what I'm explaining, Santino. The last thing that I wrote in blue. This is how my data is generated. Okay, so we take some xi, we take this inner product, we add some noise. That's the noise is IID, independently drawn and identically distributed, and that's my yi. That's by our assumptions. That's how our data is generated. Okay. What that implies is that if I give you the value of xi, you know the distribution of yi. You know the full distribution of yi. And then if I tell you that xk has some other value, remember, we just care about yi. That's our target. So I give you the distribution of xi, you're happy, you know the distribution of yi now. But if I also tell you the distribution of the value of xk, this means nothing for yi. That's just very simply put in very simple terms. Xk does not participate in the calculation here for generating yi. So given xi, yi is independent of all other x's. That's what it means. Okay, and I'm sorry. So I think this is still correct. This is still technically correct, but maybe it will help you understand if I say here that j is not equal to I, right? We're talking about other x's. For other input examples, do not participate in the data generating process for the ith example. It's only xi that participates in the data generating process. Okay. Okay, excellent. So Santino seems happy. What does that mean now? This conditional independence means that I can simplify this expression. I can actually simplify this expression, and by dropping all of the conditionals here, and actually the y's also break down. Sorry. I made a mistake. I need to erase and add the product. And so I equals 1 through n, probability yi given, I guess, right. Oh, I see. Sure. So I guess I should first motivate this first step. That might make life a little bit easier. And then we will motivate this second step. Okay, so this second step is motivated by the argument that I just gave, this conditional independence. And the first step is motivated how? Is motivated by the fact that noise is IID. So this first step, because noise is IID. That's what gives me the first step. So what's happening here? We have a joint distribution of all of the labels conditioned on all of the X's here. So this very first step, and it's an ugly N, let me fix my N. So this very first step, it's only because my noise is IID. Let's go back and look at it. Sorry, I went too far. Let's go back and look at it. We have I guess I wrote it. Yeah, I think this will suffice. If we look at this particular version of the data generating process, we said that all of these EI noise variables are independent and identically distributed, but it's the independence that we care about. Actually, that's the most important thing. So this first step is because noise is independent. So we're basically conditioning on all of the X's, okay? And then given all of the X's, does Y1 depend on Y2? Okay, so the question is, given, I'm gonna write it out on this side, given all of the X's, that's how we motivate the first step. Given all of the X's, does Y1 depend or is it independent of Y2, right? That's a simple form of the question. Okay, so conditioning on all of the X's. So if we look here again, we have Y1 equals X1 transpose theta plus epsilon 1, Y2 equals X2 transpose theta plus epsilon 2. That's how these 2 points are generated, okay? And remember, we're conditioning on X1 and X2 all the way through Xn, but X1 and X2 are what's important here. So conditionally, condition on X1 and X2, are Y1 dependent or independent? The answer is that they're conditionally independent. Why? Because the only randomness here, remember, if I condition on all of the X's, this is a deterministic value. It's not a random value. This is a deterministic value. It's not random. The only randomness here comes from the noise and the noise, the two noise variables. And because I have assumed that these noise variables are independent, then Y1 and Y2 are independent. Remember, we're conditioning on X1 and X2, which makes by conditioning on a specific value for X1, conditioning on a specific value for X2 means that this is not random and this is not random. So the only randomness remaining is in the noise. The noise terms are independent, are assumed to be independent, so the Y's are independent as well. That's how we went from this first equality to the second equality. This first line to the second line. Okay? That's it. We're conditioning on the X's. Only randomness, that all the randomness we have is from the noise. The noise is independent, so the Y's are independent. So that's how we went to this product. Okay? And now we're here, we're happy. And now we're going to use the argument I made earlier. Now we have each point yi conditioned on all of the X's. Do we need to condition on all of the X's? No, in this case, there's actually conditional independence. We could even write it as a Markov, as a Bayesnet, sorry, as a probabilistic graphical model. encoding is in the conditional independencies. But because we have, what am I doing? Because we have these conditional independencies here that we discussed earlier, we do the second step that simplifies our expression even further. Okay, so we went from a product of this form to just a product of y is conditioned on all of the x's to just a product of y is conditioned on the only on the relevant xi. Okay, just I guess that's a little bit of discussion that's a little bit too long about something that's important for you to remember. What are the assumptions on the data generating process? Okay, so at this point I can move faster because the rest is just mechanical. The rest is just mechanical. So basically what we have done here is we have written down this particular likelihood of all of our labels given all of our x's for this parametric distribution theta. We have written it in this form, in this simple form, p of y I xi conditional on theta, which can also be written in a, again, slight abuse of notation as this. I yes, well, this is, I guess it's nicer to do this, where the mean is xi transpose theta and the variance is sigma squared. So what is this? This is a Gaussian, just to explain this notation. This is a normal distribution. So the yi is distributed as a normal, which is parameterized by its mean. This is the mean, and this is the variance. Okay. Remember, it's basically we're just rewriting a version of this. Only this time we don't know theta star. We're just considering the general parametric family for arbitrary thetas, right? But this is basically what we're writing. And this thing is Gaussian, as we have noted up here already, is Gaussian with the mean given by basically this f, okay, and the variance is given by the variance of the noise. This is what this is. And now we're doing maximum likelihood estimation. We're doing maximum likelihood estimation here, and basically MLE estimate is given by argmax over this whole thing, condition on all of the x's, and it's parameterized by theta. Okay, and is also given by, for the reasons we discussed earlier, by maximum log likelihood. Okay, let's assume that this is again the natural logarithm. Sorry, I'm using a different notation here, but this is again the natural logarithm. Equivalently, we can minimize what we call the negative log likelihood. Okay, this is also equivalent by saying this is arg min of minus logarithm. It's the same thing. And here we can just finally take this form and replace what we calculated above by saying r min minus logarithm p of y given x parameterized by theta, and right, and this will be arg min theta So this P here, remember, it's a product. We have it in this form. If I take the logarithm in front of it, the logarithm is going to turn into a sum. And so what we're going to have here is basically a sum 1 through n of logarithm. I'm going to do abuse notation again a little bit and put the Gaussian in here, parameterized by its mean and its variance. Okay, but what this basically means, is that we're going to end up with a super simple form of this form. Yes. Okay, I'm skipping a step here, but basically, actually, let me just write the outline, and you can fill it in at home. It's easy, so I save some time. What is this? It's minus summation and logarithm. And what's in the logarithm? What's in the logarithm, right? It is some constant exponential minus minus, and this is the mean xi transpose theta. Oh, sorry, my bad. Well, it's the same. It's okay. So we have here yi minus the mean squared divided by the variance, and there's a 2 here. Okay, I hope I don't mess this up, but this is the standard PDF of a normal. I just substituted the PDF of a normal with mean xi transpose theta and with variance sigma squared. That's what's happening here. We're substituting the probability density function. And if I apply the logarithm, it's going to give me some constants. It's going to kill the exponential like we did before. What am I doing? Yes. No. So R min theta minus. And then what? So I get logarithm of C minus, I hope I get this right, yi xi transpose theta squared 2 times, yes, this should be right. And we can simplify things a bit. But okay, I'll just write it like this. It will be summation 1 through n, 1 over 2 times sigma squared, yi minus xi transpose theta squared plus some constant. That's it. That's the maximum likelihood estimate. And now we should be starting to realize something. Okay, first of all, this constant here, we called it a constant because it does not depend on theta. It's a constant with respect to theta. That's why we called it a constant. It contains some values inside, some sigmas and stuff, right? Some other numbers, but it's constant with respect to theta. So if I change theta as I'm optimizing theta, this remains constant. That's why I can just ignore it, meaning that the argmin of this whole quantity is the same as the argmin of what remains if I remove the constant. Okay, it's the same minimizer if I shift things up and down, basically. And now we should be starting to realize something, which is where we were getting to all along, is that this is a least squares objective. This is a least squares objective. That's what we're doing here. We're fitting a linear predictor here, this theta. That's an affine predictor. This inner product between xi and theta is an affine predictor, and we're fitting this theta, the weights, in order to minimize the squared loss, this quadratic loss with respect to the observed labels. That's it. But that's it basically. So what we are essentially doing is saying that theta maximum likelihood estimate, the maximum likelihood estimate theta is basically a minimization of L theta. And what is L theta? It's a loss. It's a square loss. And it's, I'm just going to copy it for the first step. And I've left the constant behind. We don't want it. Another way to write this, because this is a summation, I can also write this like this, and hopefully by now you're slightly comfortable with this notation. I'm going to make them bold just to signify that these are stacked values. This is a matrix. This y was a vector, and this theta has always been a vector. Transpose is a vector of all y's and a matrix of all x's, which is basically what we know and love as our square loss. Okay, so, and we're gonna solve it in a minute. I'm gonna show you the solution in a minute exactly. It's a closed form solution. But now I've been talking for a while, right? And maybe you're lost. What have we done? What are we doing this whole time? Okay. We just discussed a nice connection between or motivation for this least squares regression coming from assumptions on the noise. Basically, what I promised you in the beginning is that if I make some assumptions, then this maximum likelihood estimation principle is going to give me the standard regression loss, the square loss. That's what I promised you. And yes, the most critical assumption we made a few different assumptions, but for the fact that we got the square loss, the most critical assumption was the fact that our noise is Gaussian. We assume that the noise in the data generating process is IID Gaussian. Okay, so we basically assume that all of our points are generated in this form with IID Gaussian noise. And from the PDF of the Gaussian, we got that square. Inside the exponential of the PDF of a Gaussian, there's that square. Okay, something is raised to the power of 2. And from there, the maximum likelihood principle, by taking the logarithm, we pulled out that square and we ended up with the square loss. So we basically got the square loss because we assumed that our noise is Gaussian. The noise in the data generating process is a Gaussian. Okay, that's one little thing that we learned today. But the other reason why I like this exercise is because it gives us another opportunity to look into maximum likelihood estimation, to do one more MLE problem, and one more opportunity to look at regression. That's why it's a very relevant discussion. So, and the summary again is what? We use these assumptions that we made up here about how the data is generated in order to simplify this conditional likelihood. Given the inputs, what is the joint distribution of all the outputs, all the labels? And first, we use the fact that the noise is IID to simplify one step. Then we used for the second step the fact that each label yi only depends on its corresponding xi directly. That is, meaning that if I condition on xi, it should not depend on any other x. So then it further simplified the expression here. And that was also very, very helpful. And then from that point on, we just did maximum likelihood estimation. We just followed this simplified expression. We substitute the Gaussian PDF that we know for this conditional y given x, and we just did the simple algebra steps in order to pull out, took the logarithm, it pulled out this quadratic for us from the PDF of the exponential of the Gaussian, sorry, the PDF of the Gaussian, and we ended up with this square loss, which we rewrote in this vector form. Okay, so there's one tiny step left for us to go. I'm slightly over time, but we're going to be done in just 2-3 minutes. Let me stop here and see if there are questions about this last step or any previous step, actually. So we have this summation of these squares here, which I copied here. That's the same expression. Is it clear why it's equal to this line and this line? Okay, this should be simple to you by now. These vectorized operations, you've seen them in a few different opportunities. Let me know if you have questions about these lines, and let me make sure I haven't missed anything in the chat. Okay, Axel is asking, would we be given the PDF of a normal distribution, or should we put it on our sheet? Okay, so you're trying to budget the space on your sheet again. Here's the thing. Here's what I will tell you. Typically we give you the PDFs. Typically we give you the PDFs. For example, I would not ask you to remember out of memory the multivariate PDF for a Gaussian, but I would like you to be able to reproduce the univariate, the scalar version of the Gaussian. Devote a little bit of space on your mind and on your sheet, at least, on how the univariate PDF of a Gaussian looks like. Okay, so Mahdi has a question. So Mahdi is happy. Yes. Okay, and this thing about typically. Okay, I think I clarified what I meant. You don't need to remember anything exotic, anything multivariate. Please be able to reproduce the scalar version of the Gaussian PDF. Okay, that was it. So, okay, it seems that we're happy here with this last step, so I'm not going to spend the time on it. And then this is also, I think I'm going to leave it as exercise for home, because if I do this, and that's for, there was a question earlier, who was it? Maybe Ajimon. Was it Ajimon who asked? Ajimon asked, I think, what if we have 2 thetas? We were solving the maximum likelihood estimate problem earlier, and we said basically that we're going to take the derivative, we're going to set the derivative to 0 and solve for that, right? That will give us the answer. What if it's not a scalar and it's a vector? This is an example where it's not a scalar and it's a vector. And again, you get a system of equations. This is not the first time you've seen this. In this case, you would take the gradient with respect to theta of L, okay, and you're going to set it to 0. And basically, what you're going to get, I'm going to skip this right now because we're out of time, but try your hand at home. It's one of the easier exercises like that. You should get that this theta MLE estimate is it takes this form, but I need to be careful here with what I'm defining. So be careful. if I'm explicit here, this y is a vector of y1, y2, yn, okay? And this x should be what? This x should be x1 transpose, x2 transpose. So it's all of the input x vectors lying on their back, like horizontally, so that this looks like a bunch of inner products. The first row of x is an inner product with theta. The second row of x is a different inner product with theta, etc. So it needs to have this form for this, what I've written here, to make sense. Transpose. Okay. So then this is the form that the answer will take. There's a hidden little assumption, assuming that x transpose x is invertible. Okay, and I won't go into this detail. We should always be careful about invertibility. Okay, if you come up with this, if we have this kind of question in the exam, I will explicitly tell you that it's invertible or it's not invertible. Or actually, I will not bother with non-invertible cases just to keep things simple. You can assume invertibility, but state it. If this matrix is invertible, that's the solution. And yes, so that's right. Any questions? So, okay. So I will have to go in a little bit. I'll try to answer a few more questions, but let me make sure we're done with this particular question. I told you what motivated me for this. It combines a lot of our favorite topics, maximum likelihood estimation, regression. There was a nice opportunity to see this connection between the assumptions and a good motivation for this square laws. I came from this Gaussian assumption on the noise. So yes, so Saide is asking about decision trees. Decision trees are included in the exam, and you know, mostly in terms of the knowledge of the main methodology, like the theory. There might be a true-false question. There might be something about their complexity at that level. You might see decision trees at that level in the exam. But yes, it's in the topics that we covered. So yes. Let me see if I'm missing any other questions. Can I give intuition as to why logistic regression is linear again? Okay. All right. So that's an opportunity for me to ask people the question: when do we call a classifier linear? What makes a classifier linear? What's the main criterion we've discussed? Does anyone remember? Yes, Jake is given the response. If the decision boundary is linear, if its decision boundary is explained as is described as a hyperplane, absolutely. So that is the exact rule we have for deciding whether a classification method is linear or not. Excellent. So going back to Jake's question, why is logistic regression linear? Okay, remember, first of all, it's a misnomer, meaning that it's a classification method. But I guess it kind of makes sense because we're predicting probabilities of the positive class. So we're regressing on the probabilities of the positive class. Anyway, the thing that we had discussed about logistic regression, and I can just quickly write here. My handwriting, terrible. Okay, logistic regression. What is it? It takes this form. We basically say that the probability of the label being 1, given that we've observed the particular x, value x, is given by this logistic loss, what am I doing here? This logistic loss, I'll just call it sigma. And inside of the sigma, we have X transpose some theta, yes, plus some B, some constant. Not sure if that's exactly the notation we always use, but it looks kind of like that, right? And what does this sigma look like? It looks like this. It just squishes everything between 0 and 1. Actually, and the y-axis is off. The y-axis is off. Let me try and fix it to avoid confusing you. And very roughly, here, this will be 1, this will be 0. So basically, it takes the input, that's the input, and that's sigma of the input. What's the input? The input is this. This is what I just called the input, just for the sake of brevity and simplicity. So fine, this is a nonlinear activation function, right? Because it has this shape. So yes, it's confusing. But if it has this shape, right? We take this linear function, we push it through this nonlinear function, and it squishes everything between 0 and 1 because we want it to give us a probability. That's why we use this logistic clause. Why do we still call it a linear method? It's exactly the definition you gave above, right? Because it will actually give us a hyperplane. How do we decide to classify? We say if we want a hard classification rule, we will apply a threshold. We will say that, fine, I'll say that this is 0.5 and this will be my threshold. And I will say that if P of y equals 1 and x is greater or equal, let's say I'm going to ignore equal right now, we're going to have an arbitrary tie breaking, greater than the threshold, then say positive. If the probability is less than the threshold, I'm just going to call it negative. That's how we get a hard classification rule, binary classification rule, starting from this probability, this estimate, this prediction for the probability of y equals 1, right? And now, what's the decision boundary? In order to get the decision boundary, we have to solve the threshold, basically to take the value of the threshold and just solve this equation. It's basically everything that falls on the threshold is where we're, in between the two classes. So then you will say that sigma X transpose theta B equals 0.5. Here's a fun fact about sigma. It's a one-to-one function. It's invertible. Sigma is invertible. So I can actually denote its inverse like this. Let's say I can do this. I can always do this, meaning that this is the inverse of the function. To be clear, this is not equal to this. I'm not taking a fraction here. I'm taking the function inverse. It's a different thing. Okay. So what is this? This is a constant, and I can just take everything to the why am I doing here? Sorry, I'm starting to lose it. This was a b and this was a b, and I'm bringing this constant to the left hand side. Okay, equals 0. What is this? This is a hyperplane. Okay, so the math should convince us that in the end, what's in between the two classes. So we said if we're above half, we're in this in the +1 decision region. When we're less than half, we're in the -1 decision region, right? And if we take the value to be exactly half, our threshold, where we switch from one class to the other, that should give us the decision boundary. So solving this equation, actually rewriting it in this form, should convince us that logistic regression is a linear method, because at the end of the day, the decision boundary is a hyperplane, and it's exactly what you said. Okay, that's it. Is it when you manage to find linear separability in your feature space? So Jake has a question. What about in higher dimensions? What do we mean about higher dimensions? Let's try to understand your follow-up question here, Jake. We are already in high dimensions. We are in high dimensions. We haven't really specified, but we are in arbitrarily high dimensions, because X here is a vector of a general dimension D, and so is theta for this inner product to make sense. So
yeah, I think that last one convinced me.
High dimensions for those X's.
Your last equation convinced me. There's nothing special about the way you were treating it.
Can you repeat that, please?
I said that last line there convinced me.
Okay. Okay. Good.
Yeah.
Okay. We're happy. Thank you. Thank you. Is there an error in the if conditions? Says Aladdin. It happens sometimes. Let's look at them. This is 0. You're absolutely right. My bad. Yes, there is a typo here. This is supposed to be 0. Hey, X. This is supposed to be X. My bad. Absolutely. Yes. Thank you for catching that. And okay, that's it. I have to go because there's something else happening in 3 minutes, but you're welcome to ask more questions on Piazza. I promise to look at them tomorrow. If you have questions about old exercises and stuff that you would like to be covered. And that's it. Okay, last question. Let me address Said's question in the chat. The dimension of this kind of Jacobian, it's some kind of general Jacobian. We have dl over dA, where L is probably a function of A. Okay, so I can write it here for people watching the video later. So the question was about dl dA, assuming, I guess, that L is a function of A or something like that. And L is m-dimensional. M-dimensional. A is n-dimensional. Yes. So for general problems like that, this is called a Jacobian. That's the most general term we have for that. And indeed, okay, the most common way you will find this written, even though it's a convention and it can be written in the other direction as well, is this. You take here, you take the partial derivative. Let me make sure I get this right. L1 with respect to A1, sorry, A1, L1 AN, okay, and then L, we said M A, sorry, 1, partial derivative M, partial derivative A N, okay. So this is the most common. So it's M. In this particular case, it is an just to be precise about rows and columns, it is n rows cross m columns. Okay, but this is a convention. There are people who will change the rows for columns here. There are people who will take the transpose of this and call that the Jacobian. So we need to be careful. Okay, I hope this helps. That's right. So Lucas makes the same point. In the book, they actually might use the transpose of what I wrote. So we have to be careful. It's a convention. Like either is fine as long as we're consistent and as long as we keep track of which dimension is which for subsequent operations, for further matrix vector multiplications. We need to keep track of the dimensions always. Okay, so we don't make mistakes. Okay, and there's a nice link to a Wikipedia article on the number of operations by Aladdin. Maybe I can copy it here, paste it. Can I paste it here for people to see it on the video? A second. Come on, technology. Paste. Boom. Technology. Okay. So this should be visible to everybody. It will stay in the video for people who want to consider the link later. Okay. So solutions, we're working on them. We're a little bit behind. We're doing our best, but we're gonna get them out hopefully tomorrow. Okay. The quizzes are easier, of course. Kaggle 1 grades are not our top priority right now, but you will get, so you'll probably not get them before the final. We're prioritizing solutions. All right. I gotta run. Thank you, everybody. And I will be very mindful of your Piazza questions these days leading up to the final. I will spend some time tomorrow answering questions and then the day after. Take care. Good luck with your preparation. All right.